My name is Antti Keurulainen, and the topic of my presentation is amortised design optimization for item response theory. The other contributors of this work and our respective institutions are displayed on the screen. Item response theory is a well-known method for assessing responses from humans in education and psychology. In education, IRT is used to infer student abilities and characteristics of test items from student responses. We use the 1PL model, which gives the probability that the student I gives a correct answer for the item J. Here, Y is Bernoulli distributed outcome and theta I is the ability of the student I. The task is to infer the parameters theta and B from the observations, meaning from the outcomes of the tests. We consider a setting where only the student ability theta is estimated, while the item parameter B is treated as a design parameter. We recast experimental design for IRT as a reinforcement learning problem, which allows for amortizing the design optimization, which facilitates real-time, adaptive and sample-efficient assessment of student abilities. We train the system in silico and use the ground truth parameters from the simulator as prediction targets during the training phase. The reward for the RL agent is the squared error between the true and estimated student ability. Consequently, the agent is rewarded for selecting experiments that lead to accurate parameter estimations. The training and deployment architectures are illustrated here. In the training phase, at the start of each episode, the simulator which simulates a student is initialized by sampling new model parameters from the prior. The RL agent makes requests for the item difficulties and the simulator produces an outcome using the obtained design and sampled student ability. In the deployment phase, first a maximum likelihood estimate for the item difficulties is produced by using stochastic gradient descent. Once the estimates of the item difficulties are available, the item requests are mapped to the closest items from the existing dataset. We compare our method against random designs and against optimized non-adaptive design strategy. The left panel shows the true student ability against inferred ability. The middle panel shows the ability for random designs and the right panel for non-adaptive optimized designs. The results show that our method outperforms non-adaptive and random design strategies. For more results and details, see our conference paper. We introduced a novel method for amortized experimental design and parameter estimation for the IRT setting. Interesting future work would involve testing the system in a real-world setting with human participants. Another interesting avenue for exploration would be to extend this method to joint experimental design for both student abilities and item difficulties, thus stepping towards more open-ended generation of learning content and assessment methods.